That's my website. I'm for hire. All right, so let's actually start with an example. On the drawing of interesting insights from measuring the coverage. So this is a binary search that I borrowed from the internet. Pretty straightforward stuff. You know, we make a local copy of the begin and end range of our input array, and then we search it while checking, is this the needle, the X we're looking for? Okay, so we have a constant haystack here, sorted, and a test suite where we look for the, it's a pretty solid test suite, right? We have 6 test cases, looking for the smaller than smallest, the hit left, the miss left, larger than largest, hit right and miss right, okay? And you're thinking, you know what, this isn't too bad. So we run this. Sorry, BS1. There will be more. And then we have a look at the report. So this is my program zgov. And here is the report. We have, or the total. So that's 15 out of 24 paths covered. We don't measure line coverage here, but we do measure block coverage. And if you cover all the blocks, you do cover all the lines. From the line coverage perspective, this is 100%, which is not bad. You know, we do all of the blocks and we do all of the edges. But we only have 15 out of 24 paths. Okay, that's not great. So what we can do is we can brute force it, because we know our domain is from 0 through 5,000, roughly. So we test it, right? We carpet bomb the input space. Takes a little while, and then we measure it again. Okay, lovely. We go check out our function, and we have covered one more path. Okay, that's not great. So this actually provides us with an opportunity. So look at that. The 6 there has been executed. What is that? 172,876. What is that? 172,876 times. And we've only covered 2/3 of the paths. Okay. Now, what I would like to do at this point is to figure out why is coverage so poor. And what you can see in zgov here is that I have a very primitive thing. Is this covered? So the path we're looking at now is the one that is emphasized, right? This one we haven't covered, and its sibling path here. So this is the case, let's see, where on the first iteration, you know, even before going into the loop, the minimum element is larger than the maximum element, right? This is a user-provided parameter, and it's really nonsensical when it's negative, because an array cannot have negative length, right? Okay, so that's not great. There's another path here that we can look at where we found the element, but there is another check here at the bottom, and you can see it in the source too. Hang on. Where we're saying, is this the element we were looking for, or should we return not found? But we already found the element, so this check will never be false and return not found. Okay, so we have a contradiction in there. This path right here, it starts at 3, which is where the element we're looking for is larger than the middle one, and we have the search space from the left. And then immediately the loop breaks because we searched the whole range and not found the element, and we fail this check here, right? So we broke out of the loop in this case because the range was exhausted, or we've searched the whole array, But at the same time, we're now checking again, is this the element? Right? It can never be the element. That's why we broke out of the loop in the first place. OK, so let's move on. We can do better. So hang on, where we're at. So let's fix this. So what we've done here is that we've changed the comparison to only be, are we still in the range? And then we move the check, is this element that we're searching for inside the loop, and then return, if it is, right? So we don't do this awkward thing where we break the loop because we found the element, and then we need to check again, is this the element? We just return right away, because there's nothing more interesting we can do here. OK. So we can make that and run the same thing again with the 5,000 elements, right? Right. Takes a wee bit of time, and there we are. OK, so we open that one again in setgov. All right, 17 out of 18. That's a lot better. Now what has happened here is that we've actually restructured our program a little bit and moved what is inherently a redundant check. We have one path left, which is the one where the list is just empty, and we just skip it altogether. Like we're skipping the loop. And in order now to actually satisfy coverage, we've improved our program, I think. This is much simpler, it's much easier to work with. Interestingly, this violates MISRA. So if you're in safety critical systems, this isn't allowed. You have to do the other thing. Yeah. We can actually add a few tests to achieve 100% coverage, and now we just update the test suite with the missing 2 tests. See here, where the list is empty, and where we hit the element in the middle right away. There we go. OK. And if we would run that, we have covered all 18 paths with the test suites. We needed 2 more tests. And we were able to identify those because we actually used the coverage to figure out that the structure was wrong, so we could simplify the structure. What's our lesson here? When you're doing multiple checks on dependent values, which is an example of, we got a structure that we originally... Does this keep cutting?
Yeah, it keeps going in and out.
Am I doing something wrong?
I think I heard before it's a bad wire from the mic.
Oh, OK. I'll try and be a better wire. OK. Real programs essentially often have this kind of behavior, whether you intended to or not, right? So some of this might be... Hello? Did the sound technician go away? I don't know. Function call, you might actually... So what I would like to say is generally, so far, we've been holding it wrong. Usually when coverage is measured, it is an app, and it's a sort of matter of fact. I'm going to try and really scream. I'm sorry, front row. This isn't working. It's usually done in this sort of after-the-fact manner, right? So you're writing a program, you're doing all kinds of tests, you're doing bits and pieces, and then you're measuring coverage once. Yeah, it's whatever, n% lying something, and then you're done. Good job. Or you're putting in your CI pipelines and say, if the number ever goes down, we're blocking the merge. And I think that's a mistake, largely because it would be very easy to cause this false positive where we make a good change to the code, but the ratio changes because, for example, your percentage drops because you remove bad code. So your coverage is actually better, but the number is wrong, and so the test fails. It stalls pipelines, all kinds of awfulness. On top of that, it might require expensive setup, both in infrastructure and in code, to do the testing. That doesn't actually provide you any value. So what I would like to go back to there is that coverage is not really coverage is not the goal. Right? Coverage is never really a good goal. Our goal is good software. Right? And what I want to come back to, and what this talk is really about, is figuring out how can we apply coverage in order to get good software. So I don't think it's a controversial statement to say that testing is correlated with quality. There are some diminishing returns, but testing is not the goal either. Right? The goal is still good quality. It's good software. So why do we bother with testing in the first place? Like, why is moving tests up and down in the programming pipeline? So do you write your test before? Do you write your test after? Do you do like very religious TDD? Do you no testing at all? Is it all manual by sending it to some test factory somewhere? Do you have a QA department? Do you not have a QA department? How does that affect quality? And I would actually argue that in many cases, the process of testing alone can be sufficient value to actually, achieve your goals, to get better software. The job that started this journey for me was issued by NASA. So in a way, testing for them is what brings us closer to the stars, literally. What I will say is that the way we should apply coverage is to guide testing. Right? We don't measure coverage for the sake of the coverage. We measure it to guide testing. Because coverage alone doesn't really find any defects. It doesn't find any problems on its own. Testing does. And the coverage is another tool to actually evaluate how well are we testing. What does that mean? Are we testing what we would like to? It helps identify problem spots, blind spots, both in the implementation, but also in the specification, which is arguably the more interesting one. And finally, the goal is just good software. I'm going to go on just reiterate, I've said this probably 1,000 times in this conference, that line coverage is just a bad metric. Try again? Oh, okay. So if this keeps cutting for you, I'm sorry, then it's not the wire here, it's somewhere else. Okay. So line coverage is a bad metric. And has a poor context window, but maybe more importantly, what is a line anyway, right? So we don't really program by lines, and I have a great example on that. But fundamentally, lines truncate the resolution line is truncating a multi-feature construct into a single bit of information. Did you do the line or not? And then I have an example here of a program. Hang on. Where we can achieve line coverage. I think by running this, we run a line. Is it well tested? Maybe, maybe not. But what is a line, right? The concept of line is just odd. You would get farther if you talked about statements, but even that has some problems. So, yes, man, you can of course tell what this program does, right? Actually, let's run the version with coverage. So this program obviously does the Amiga demo, which you could tell from the source. Now, it's a pretty hard to decipher program, but some of it becomes easier to work with when you look at it as a graph. At least you can kind of follow it, right? Okay. So block coverage is a better metric to use as a sort of baseline. And I think edge coverage even more. But this is the bouncing ball. Right? You can by rendering it as a graph, edges show up. So that's that one. As a side note, if your targeting coverage is 100%, any other number is nonsensical, right? Because the problem is that not all constructs were created equal. And it's pretty easy to have a high percent number that is not 100% that still misses all of the important bits. Any other arbitrary target is just way easier to game. I'm not so worried about the target because what we should use is we should use these reports to inform ourselves about our programs, right? An example of that, so in safety critical systems, those that you'll find in cars and trains and aircraft, that kind of thing, they all require 100% modified condition decision coverage for their critical bits, right? So there they do have a target, which is just by regulation, which is 100%. If that had been 80%, I can guarantee you more planes would have come falling out of the sky, right? It would be gamed and we would have way worse control systems. Do I go on and on about? There's Goodhart. Now, it was originally phrased is that any observed statistical regularity will tend to collapse once pressure is placed upon it for control purposes. He was an academic. Goodhart's law has been rephrased slightly for various applications. To be more specific, tricks of scientific evaluation are bound to be abused. Goodhart's law states that when a feature of the economy is picked as an indicator of the economy, then it inexorably ceases to function as that indicator because people start to game it. I included that because he too uses the phrase to game it. Kevin, that Goodhart's law measure is inexorably, if ruefully, becoming recognized as one of the overriding law of our times. Ruefully, for this law is a law of unintended consequences seems so inescapable. But it does so, I suggest, because it is the inevitable corollary of that invention of modernity, accountability. Jon Danielsson phrased it as any statistical relationship will break down when used for policy purposes. This is how coverage is often used. Yeah, need 100% to pass CI. Thank you. This is how it's commonly stated: is the target ceases to become a good measure. So, what this really make coverage the goal, the target, you make it the goal. But the goal shouldn't really be, it should be the quality, it should be software, right? So that doesn't mean that we should stop testing or stop measuring. It means that if we're using coverage as a proxy for quality, we're not actually going to get the quality, we're just going to get the coverage. Which is still applying to more deliberately, because it's a form of observability at the end of the day. So when I was researching this and gathering the exact quotes, oh, hang on, yeah. If you go on the wiki, it says that you shouldn't confuse it with the Godwin's law, which says that as an online discussion grows longer, the probability of the comparison involving Nazis approaches 1. So don't do that. Okay, so let's talk about quality. So how does coverage contribute to quality anyway? So it works on two axes, I think. It works on defect and bug detection, which is like you've written some code, you try and test it, you use the feedback from the coverage to test it thoroughly, and then you find your defects. And the other one is as a design feedback. So we have the two qualities of Axis. So with the bug detection, we have the 90-90 rule, right? Which states that the first 90% of effort finds about 90% of the bugs, and then the next 90% of effort finds the remaining 90% of the bugs. And there's something to be said about, like, the more you're testing, the more you'll find. So I suppose the secret to an unbreakable, bug-free program is to just not test. There we go. I didn't have written it down. There we go. Okay. The other one is design feedback, right? So what we want to do is we want to exercise the structure. And exercising the structure, it forces us to think about the relationship between our inputs, the pass through our codes, and then our output. So the question is, like, did input X actually go through path A? Did I intend it to go through path A? But no, it was actually intercepted by a condition that was too wide, right? We got we used a lesser equal where we should have used less, for example, right? Oops. Now you can actually detect these relationships, and you can verify your assumption. And then there's a coverage metric. Does it really work, right? So the difficulty and arguably the value comes from controlling different constructs, right? So we're going to look at some of those, but I would actually defer some of this to a study I found from 2000, which is an empirical evaluation of the MCDC coverage criterion on a satellite project. It's between some French institution and MIT, I think. So we're going to do some more quotes. These are the last ones. But they found that although MCDC coverage testing took considerable amount of resources, so testing is expensive, right? It was not significantly more difficult than satisfying just a condition decision coverage. And it found errors that would not have been found using worse metrics, right? They also claim that the white box coverage analysis revealed some parts of the code were not fully covered, according to MCDC, by the black box testing. As might be expected, these parts primarily involved error handling. This fact is consistent with data showing that a large percentage of operational errors found in requirements involve the error handling routines, which are often not well tested. Does that sound familiar? These routines are difficult to test during functional testing as they involve unexpected and erroneous behavior of the software, the environment, or the underlying digital hardware, such as bit flips caused by EMI. This is obviously a satellite problem more than you would find here on Earth for the most part, but, you know, it's still real. So the MCDC coverage evaluation also uncovered errors in the specification. An error in the code involving the paddles deployed variable caused one branch of the mode switching logic, which goes from 2 to mode 8, when the cameras are tracking to be taken. This branch was not included in the specification, so the problem was not noticed during black box testing. So in this case, you actually had a case where the programmers who did this found a case that wasn't in the specification, but they coded it in anyway, because they're, you know, bright bubbles that wrote some nice code. And they fixed the specification by measuring and doing the coverage. They figure out that, hey, this is actually a thing. Okay. So they found that for the, however you say it, HETE2 software, all the additional tests required to satisfy MCDC criteria were directly linked to an important feature of the software. And this is, I find this very often with these strict coverage, is that they add something, you know, beyond the target metric. They actually find problems in the spec or in the implementation. So let's talk about code complexity. We do have an intuition program on code. There are with common problems like more bugs, hard to understand code, you know, difficult to test. I've found that prime paths, just measuring them, they map quite well to that intuition. So a function that I feel is complex usually have a very high number, and the other way around. And sometimes I've been surprised where I have function that felt kind of simple, but then it turned out that when I studied them, they had a lot of subtle complexities that the path coverage actually captured for me. So there are a few traditional ones. We'll go through them real quick. Past our intuition, you have the cyclomatic complexity. Now this came about in the mid-90s from a paper by a man called McCabe. And it's defined as E minus n plus 2p, where E is the number of edges, n is the number of nodes, and p is the number of connected components. So already here we're talking about graphs, right? So from that paper is a verbatim quote. Once the code for a software module or file or subsystem or function is finished and processed by automated tools, reworking it to reduce complexity is more costly and error-prone than developing the module with the complexity in mind from the outset. So pretty much, if you measure things that measure the complexity early on, you will probably not make it as complex as if you do it after the fact, and you will definitely not change it once you've written it. There are some flaws with cyclomatic complexity. It doesn't distinguish the type of control flow, so loops and ifs kind of get the same number. And it also doesn't consider the direction of the control flow. So this has been tried to be fixed with something called n-path complexity, where they measure the number of acyclic execution paths through a function. There is another metric called the AC path complexity. We try to fix a flaw with that. By dealing with what they call back jumps. It is fine in terms of syntax and control flow, which frankly I think is another. So let's move to prime paths. Prime paths are maximal paths and simple cycles. Okay? When you analyze the control, or when you look at it as a control flow graph. Simple in this case means that no vertices are repeated. And the complete metric for this means that we're just counting the number of prime paths in a function. There can be quite a few of those, especially for complex functions, but in practice I find that still an acceptable or a useful measure of it. So let's talk about a development loop. Usually we're doing this sort of write, compile, test, write loop. So write, compile, test. So test might be something like running your test suite, but it could also be running your program by hand, maybe just compiling. It depends. If you have a test suite, you run it, right? I suggest we often extend this to a write, compile, test, measure loop. And we add a measurement step as sort of part of the test step. TDD does propose that you always write a failing test first, and then observe that you actually change the behavior. If you have measurement, that means before running your test, try and figure out which path it should be taking and verify that. That has surprised me very often. That's not the case. That I had misunderstood something and my test wasn't actually good enough. So unit testing really is about poking the program, hammering it with specific data, and just observing how it responds, right? And to me, coverage really is a mapping that it explores mapping that responds to the program structure. So I have an example where we're going to do some coverage-guided programming. So I have a hang on. I have a program here called the leap day, which is not great, right? Jason does not approve. Okay, we're writing a program. We're writing a calendar, and we just want to know if today is a leap day, right? Is today the leap day? This is our first iteration. We've figure out what time it is now, and then we check in our local time if today is February 29th, because that's the leap day. And then we have a test, is the leap day today, which is usually not the case, right? So this test is broken. It fails on the leap day. And the thing is, and this is a trick that I learned from John Carmack, who I think subscribes to this religiously, is that time is an input. And in this case, we can't actually control the time. So we, oh, hang on. So we built the leap day. I mean, obviously this, oh, hang on, leap. We test it and it's fine, right? The test passed. It didn't trigger the assert because today is actually not February 29th, right? But we can look at the structure. Let's see, leap. And was this what you expected when you read the code? So what has happened here is that the compiler breaks the Boolean function into a system where it evaluates each of the terms on their own and then uses the flow between them. This is how it implements short-circuiting. So if the first check would be false, it would immediately jump to the else case where it returns true. There's a hidden assign false in there, right? But it has a straight line flow until it actually starts evaluating the local time, the TM struct. So in this case, you can see that the graph, it widens before narrowing back in block 9, which is the performing of the return. This edge here is called a bridge in computer science, or an, what is it? Yeah, a bridge. There's another name, like isthmus or something. And this is an edge that all the paths have to go through. The paths for all the subgraphs must go through, right? So bridges are markers, really, for natural places to split functions or where to make strong assumptions about the state of our program, regardless of where it's coming from. So your pre and post conditions. This is the truth table for the leap day. It's only true when both the TM is 1, the day is the 29th, and the month is the February, and the day is the 29th. With short-circuiting, these are the interesting inputs, right? And you can see the 4 bottom rows, they just collapse, right? They're pretty much all the same. So this is with short-circuiting and masking from MCDC. And all of a sudden, you can kind of see where our interesting inputs are. If you collapse this table, this is what you get. So these are our 4 cases that we care about. So we remove all the duplicates. With short-circuiting, masking, MCDC, this is the relevant truth table for this function. And this actually maps to the paths through the graph that we saw. Okay, so let's try and fix this, because we can't have a function that fails on the one thing that it should succeed at, which is to detect the leap day, right? So we fix this by by making time a parameter, right? Just pass in the time by value, because now we can control it. Now this is not controlled by the system. Setting the system clock to run a unit test is a bit aggressive. But now we can control it. So in this case, 2024, it is a leap year. And then we design a test. We test it where we set the day and month to February 29th. The rest of the TM struct now is garbage, or it's 0, but it's meaningless, right? But that's okay. Sorry, this is February, but not the 29th. And then we also test it with the 29th, but not February, which is another case. And finally, where it is the 29th of February. It's a pretty decent test. It's a leap year. It's not a leap year. It's actually, we didn't test the not leap year even. But where the month and day are both correct and not correct at the same time. Okay, so we can actually now run this. And look at the report. All right, lovely. So a graph is the same, but we covered 3 out of 4 paths. Okay? So we've done this path, and this path. There's one that's missing. Oh, yeah. So in this case now, we have 100% line coverage, we have 100% in statement coverage, we have 100% edge coverage, but we don't have full path coverage. We can add a case for the where the month is not February and the day is not 29th, but honestly, that wouldn't actually add any value to us, right? Because you see now, that wouldn't be a path that we would now take. So it's informing us that that part of the test suite is actually fine. But it also shows that the case we're missing is where TM is the null pointer, right? And what is neat about just moving the time out is that we're not actually even calling time anymore. We're just constructing very specific values that we know can be returned by time. Yeah. When I was creating this example, I actually had a really hard time to cause local time to fail. So when time, the call fails, it returns -1. But if you pass -1 to local time, you get a local time that is valid. That local time doesn't fail, which surprised me. It was really hard. It turns out we need a missing case, which we can construct by giving it a garbage time. I stole the case from Musso, and that caused it to. Okay, so if we run this, we'll have 4 out of 4 paths covered, but still the test feels kind of bad, right? So this is the case where I say, you know what, full coverage, we should be happy. But not really, because this test still feels bad. We have a garbage input that caused the function to succeed, but with a good value. And our goal isn't coverage, it's good software. Is this a good function still? No, I don't think it is. Right? We're going to see how you can improve it. But the original problem would only occur on the 29th of February. And part of the problem now is that local time can still fail, right? So we're giving it as a garbage value, and we're getting we're causing it to fail, but the test still returns true, right? Look at this. Hang on. The test returns, yeah, it's not the leap day. Okay. So how can we fix that, right? How do we fix that? Well, the solution is, so the fundamental problem is that the Boolean isn't wide enough to capture the case where the local time function fails. Because the local time function to fail, but with an input, right? So what we can do is to fix it by not calling local time. And take that as a parameter instead. We just reapply the same technique. We can reasonably assume in C that pointers that we pass to functions are pre-validated, right? This function is actually pure and stateless, and the validation and reporting happens somewhere we can handle it. And what's even is that now we can replace the call to local time with a call to PM time, some other. So we actually. So the question then, is this post code better? I would argue so. It's definitely easier. It does offer some more flexibility. We control the source of time from the outside, but it is stop if you just. So this is an example where change the structure of the graph to give us a better program. Like we're using the information from measuring the coverage and from measuring the structure of the program to inform refactoring. I have an example needing use to do that. We're running a little bit short on time, so we'll probably skip some of them. But since Rust, should we look? So there is an experimental front end to GCC. So I've written a Rust program. by 2 function. It's not a very good one. But yeah, it is total, since that handles all valid I32s. There's something. Rust is safe. I also have a very elegant way of computing the absolute value. So we, what I think is neat is that Rust 2 with GCC. So notice this flag here. In order to build with this, you need to pass frust incomplete and experimental compiler do not use. So don't put this in production just yet. But there's a taste of what's to come, right? So let's look at the absolute. Isn't that neat? So this is the structure, and this actually looks very much like what a two-term condition graph would look like. So this is how the Rust compiler then actually interprets these if-else ifs. So it tries them in order, and I can imagine that actually being well specified by Rust, that it has to try the cases in order. And this is actually really good design feedback, because if you know that one of your cases is very much more likely than the other, put it on top. Okay. I was going to do a whole on how to explode your code, but I think we're going to. But what we can do is we can look at some exceptions. That would you ever? Who are you familiar with Duff's device? If you've been around the C scene for a bit, you might have seen it. I see some nods. I like that. With the remainder operation on the switch. And in the switch, you have a do while. Okay. So you want to see what it looks like? This is just tried for fun and figured, what if I throw Duff's device in there? So it looks like this. Go through the start, you consider this value, and then you make 1 out of 8 jumps. At which point you have a goes down until you make a decision at the post, because it's a do while, so it's at the end. In which case you decide whether or not to loop all the way to the top or to exit. So this is a do loop unrolling, where you first need to find your whatever not divisible by 8 block. Do that and keep doing the loop unroll loop by calling it 8 times. And I was so happy because this representation just it is a bit clearer, but it's not as beautiful. This is the send to. You just split the two constructs. I get exceptions. At the same time. So we have 2 functions. We have unsafe at and checked at. And the unsafe at is just C, really. That's array indexing in C. Check that just checks that are you within the bounds or not, and if it just throws an exception. So let's assume that we would like to cover this. Throw one. There we go. And with the unsafe add, it's forward. Right? Doesn't matter what you do, it will just jump off to the address and go ham. So this is what you would expect that would happen. Covering this is easy. Line coverage, branch coverage right now. You're safe. Now your control flow graph looks like this. So what's happening here? Well, so you have the case where the if checked the case to the C and you just go straight. But now it's fine because you covered it, right? And in the other case, you're throwing an exception, which you're constructing and then ending up in a throw. You're not actually returning from that function when you're throwing, right? You're not actually going through the return, so this has a different exit point. And this is the reality with C++, is that it doesn't take much for control flow graphs to become horrifying.
Why does it look like the same blocks twice?
Like the return one is.
Oh, wait, 3 and 4 versus 6 and 7, yeah?
Yeah. The mode where those. Thing, and then you would do the jump, which is, from a control flow perspective, different operations, which is why it's a quirk currently. Then that throws. Right? Let's look at that. So in this, where we just try and accumulate with check that, and whenever it fails, we just don't do anything. Okay. That looks like, and what's cool, or what's neat here is that these are now sort of parallel branches that you could take. This is now just regular control flow, as is intended. Like, this is what catch is supposed to do before returning back, being done. Okay. So that's what happens when we catch the exception. So a bit of a confession time. I have written code where I thought an exception would be thrown and it turned out it didn't. So exercising exception paths is actually quite important. There are very often bugs both when handling exceptions and when throwing exceptions. So it is in that they're in the graph and that you need to cover them for the purpose of path coverage, because there will be problems there. Even if you think, oh, there's an exception, we're just going to abort anyway. That might not necessarily be the case. So you need to test it. Because exception paths are almost invisible in source code, it's kind of easy to forget that they're there, which is kind of their point, right? But they light up when you're doing it with coverage. There's another interesting case that can come up, which, hang on. Throw 3. Anyone want to take a? You don't have to. It's not obvious at all. It looks like this. What happens here? So the right end is 6, 7, and end. That's still the same. But what happens in block 4? This too is another subtle problem. So the problem is that you're constructing an exception which takes a string, which is a string copy, which is a heap allocation, which can fail. So now your exceptions can throw exceptions. Do you want to cover those? Okay, so this is a real problem if you're going for the 100% coverage. But look, we have only have 3 paths here, and one of those paths particular is pretty hard to cover, right? How do you cover the path that only happens when the string allocation fails because you run out of memory while you're processing the exception? Turns out there is a way. We're running out of time, so I'm going to be quick on that one. But what you can do is what is called replacement functions. There are 3 of them in the standard library as of 23, I think. Up until then, it's just 2, which is operator new. You can implement your custom operator new and link into your program. And what I do in this one is that in my tests, I set up a counter, say, fail the nth allocation. And then I keep on increasing the allocation allowance until the function succeeds. So John Lakos spoke about this at ACU a few years ago, and he refers to it as orthogonal perturbation. 2022 he did. Is that you can do exactly this and just keep on increasing the allocation allowance until it goes through. And at that point, you will have exercised all of these exceptions. It's actually a pretty neat technique, which is supported by 6 lines of horrifying code. So in my test suite, I very often do this. There is a special section at the end where I just run from 0 through n allocations just to exercise them to make sure there's nothing else going on. Turns out it's actually quite cheap in practice. Okay. There are other ways to deal with allocation failures, but it's difficult in C++ because it is implicit, but you can use custom allocators, which is a really cool technique. Zig, the language, is putting those front and center. But generally, instrumenting global states is difficult. We're gonna skip a bit ahead. So going back to that, why I'm care about the exception, and it goes back to this, right? Is that this is consistent with data showing that a large percentage of operational failures, operational errors found in requirements involve the error handling routines. Test your error handling routines, or don't handle the errors, in which it's fine. Okay. Both the techniques I've shown here so far, they're kind of dependency injection, and a lot of how to test or write for coverage comes down to either simplify your program and inject your dependencies so you can synthesize the failures or the modes that would cause specific paths to be taken, and especially true for the hard to reach ones. And what I find is that for code where you actually try and handle errors, line coverage is a miserable thing to achieve if you have error handling, because then you still need to synthesize the errors. And by the time your test suite actually synthesizes the errors, you can actually go for path coverage, right? That is the difference between these 2 APIs, right? So in one case, you have a function slurp, which just opens a file at a path, reads all of it, and then returns you the byte vector of the contents. You slurp the file. If that makes a file handle instead, you can rig the file handle to cause errors, right? But you can't do that if you're letting the resource be controlled and owned by the function itself. So you would sort of split your API into these 2 bits and pieces, and one that just consumes them. This is how you would do it with a file. If it's just have something that you can set for anything but test is you can do link time. Hang on. So where are we on time? We're at 5 minutes. I'm going to do some final thoughts, and if we have the time, I'm going to show you link time function wrapping, because that is horrifying and gorgeous at the same time. Okay, so I just want to do some final thoughts on this. Is critical in engineering. It's one of the things that we do, right? Measuring it is just essential to do. And testing things is also essential in engineering. There is a cool video from Boeing, I think, where they want to test their plane. Like, how much stress do the wings handle? So they build a plane, put it in their hangar, 2 lifts on each wing, and just keep on bending the wing upwards to see at what point it passes the threshold, and they all celebrate, right? So they literally built a plane to break it. Than the most of the unit testing we do here, but I mean, this is essential if you want to do good engineering and make safe things. Now, coverage really boils down to this is a tool for observability and measurement for testing. So what we really need to be careful about is to make the measuring a target on its own, because then all of the value, all of the effort you put into the coverage is going to go right away. And the same thing applies to testing. Testing is the goal. Software, quality software is the goal. And I think it's unfortunate when we end up writing bad software but with good coverage, when it should rather be the other way around. All right, so C++ you can override the new, extracurricular. You can override the new. What do you do with malloc? Right? So I just want to show this because I just think it's cool. So I have a function here, alloc called C, or a file, sorry, called alloc.c, which does the same thing. As it fails malloc after n attempts, right, with the counter. And the GNU linker and I think the LLD linker, but not mold, and at least some of the linkers support this function where you can, or this feature where if you call your function _wrap _ the name of the function, you can have the linker substitute every call, even in third-party things that you link to, with calls to this function instead. And that allows us to, at link, substitute our own function in libraries we don't really control, like you do with operator new. So just figure out what's the make target here. Yeah, okay. Well, when trying to malloc in the first place, because the counter starts at 0, right? Because I want to make sure that this fails, and getting the global allocator to fail doesn't happen too often. Like we rarely run out of memory. There we go. You pass the wrap flag and you substitute the malloc, right? So we can run it. Fine. The first allocation, fine. The second fails. And oh, I didn't even instrument it. But yeah, so that's a pretty cool technique when you have these functions that you don't really control, but you want them to fail because your error handling depends on this one failing. And with that, you can achieve coverage in the most difficult to reach places. All right, it's time for lunch. I will be available for questions. Thank you very much.